In example 6, we have a different question which is telling us to solve the inequality. Solve the inequality modulus of 5x minus 1 is greater than 3x. We have to take care of this part of the question because it's now not equals to, is greater than. You know, we've been dealing with equals to, and equals to just need us or require us to just give us a specific value of x, but with greater than or less than, it's a region and we have to give a wide range of x. So let's see. Again, we need to sketch y is equals to 5x minus 1 modulus. And of course, naturally, the way we have known how to go about it, if we have x and y, we can talk about when x is, let's say, minus 1, we have minus 5, minus 1, minus 6, and the modulus of y simply becomes positive 6. When x is 0, we have y minus 1, and therefore y modulus is 1. When x is, let's say, like 1, we have 5 minus 1, which is 4, and of course modulus is also 4. When x is 2, for that matter, we have 10 minus 1, which is 9, and the modulus is 9. But it is most importantly the turning point. Where does the graph again cut or meet the x-axis? It meets the x-axis when y is equals to 0. So we have to talk about 5x minus 1 is equals to 0, and 5x is equals to 1, and x is equals to a fifth. It is as this aspect that the graph cuts the x-axis, and it will be now the vertex of the graph. You can already see when x1, 2, 1 and 2, minus 1, minus 2, when x is a fifth, we have y being equals to 0. When x is 1, let's talk about 1, 2, 3, 4, 5, 6, 7, 8, and even 9. When x is 1, 1, 2, 3, 4, 5, 6, 7, 8. When x is 1, we have y equals to 4. When x is 0, we have y is supposed to be negative 1, but because it is module, it's going to be positive 1. When x is negative 1, y is supposed to be negative 6, but y module is now going to be positive 6. So we have our graph. We have our graph that looks like that. And the graph you will see here, y is equals to 5x minus 1 modulus. In the same axis, we need to plot y is equals to 3x, and it goes without saying x and y. When x is 0, y is 0. When x is 1, y is 3. When x is 2, y is 2 times 3, which is 6. So very fast, when x is 0, y is 0. When y is 1, when x is 1, y is 3. Y is when x is 1, y is 3. When x is 2, y is 6. So we are going to have a graph that is going to appear to look like that. So this is the graph of y is equals to 3x. You can already see that it cuts the graph at 2 points, that is 1 point and another point. Our graph is not very, it's not to scale, so this point does not suggest that it is along the y-axis. Calculations will show us where this point lies. But of course, we have point A and point B. Having done that, of course, we need to differentiate the two graphs. The black graph is the modulus 5x minus 1, and the red graph, let's talk about the red graph here. Let's shade that red. It may not be very clear. We just want to differentiate the two graphs, because when it comes to greater than, then we are required to show clear difference. All right, having done that, we now need to talk about at this particular point, or at point A, we have negative, because it's the moduled part, we have negative 5x minus 1 is supposed to be equals to 3x, because we are talking about a point of intersection. So opening this graph bracket, we have minus 5x plus 1 is equals to 3x. What's the meaning of this? It means 8x, when we take minus 5x across, is going to be equals to 1, and x is going to be 1 over 8. So that is called the critical value of x, which will always appear at the point of intersection. Let's talk about at point B. At point B, we are talking about the original part of 5x minus 1, so it's not moduled. We have 5x minus 1 is given by 3x, and of course you're going to have 5 minus 3x, 2x is equals to 1, and x is equals to a half. This is another very critical value of x. But when you revisit our equation, we are talking about greater than. And we have said that the black graph, this is the graph of y is equals to the module 5x minus 1 module, and the red one is y is equals to. So if the module part is supposed to be greater than the 3x minus x, all values of the module part are supposed to show something greater than the values of y is equals to 3x. So every region where the black graph is above the red graph, that makes a lot of sense. For example, this particular point, when x is supposed to be negative 1, at this particular point, the value of y, you can see it's positive for the module part, and the value of y for the linear graph, y is equals to 3x, is negative. So this particular point makes a lot of sense. This particular point, if you look at it, the black graph is below the red graph, so it doesn't make sense. So what are we going to say, and how are we going to answer our question? Since this is a critical value, for all values of x less than 1 over 8, for all values of x less than 1 over 8, all the values of y of the module part are greater than all the values of y for the linear graph. So we can already say x is greater than 1, not greater than, less than. For this to make sense, x is supposed to be less than 1 over 8 for all values of x less than 1 over 8. Because we could even take minus 2, we could even take minus 5. We expect the module part to be a very big positive number, and we expect the value of y in the linear graph to be a very big negative number, so it still makes a lot of sense. Let's go to point B. You can see from here, moving forward, for every value of x that is greater than a half, yes, the values of y of the moduled part, they are always greater than the values of y of the linear graph. You can clearly see from here, moving to the right, the black graph is always above the red graphs, and therefore x is greater than a half for all these values of x this particular relationship makes a lot of sense. And that is why those are our values of the question that we were looking at under example 6. All right?